so a lot of people have been asking for an update video. Now, I don't think we're quite at the place where an update video is appropriate, but there's been so much concern, I thought I'd do an update video anyway and show you where we are. And I appreciate the concern, I really do, thank you very much, but we haven't been knocked over by a bus, we haven't disappeared, and we haven't stopped working on what we're going to work on. One thing to appreciate really is that there's only me and Steve doing this, and we're working on extremely tight budgets. I mean, we just don't have the kind of money you would need to be able to pay everybody to do everything. One example of this is verification. Of course, we need verification of this battery. And we've begun to organise verification with the National Physics Laboratory here in the UK. And the reason for that is it's the National Physics Laboratory. It's a very prestigious name. So when they verify our battery, then it's going to be ground and solid and true that that is what the battery does. So having the right people to do your verification is very important, and we've gone with, or we're trying to go with, the National Physics Laboratory. They've actually said yes, and we're in the process of negotiating what work needs being done and how much that is going to cost. Now, we know it's going to cost around about £10,000–12,000. That's a lot of money, but it's also very important. The other thing about it is they can't fit that work in until November, so it takes a little bit longer to do such things, but it's so important, we're quite happy to do that, so we have that to pay, and it's going to take us that long to actually get the verification begun. It's probably going to be December, January before that verification report is out. But that's one of the reasons it takes so long to do these things. We have to fit it in with other people's work, we have to be able to pay for it, and that means we have to generate that money to pay for it, and getting that money to pay for it takes time. There's only two of us, so it takes time to do everything, so everything takes longer. Now, that's not a bad thing. I mean, Steve and I have been at this for what, 3–4 years, something like that? That's fast. When you think that other battery development takes 5–10 years, and there's whole teams with hundreds of thousands of pounds of budget to throw at it, it's fast, it's quick, it's kind of awesome actually. So that's the sort of things that you're looking at when you're looking at what we're doing. Now, the other thing is we obviously have a criteria for what it is that we're going to do. So we've made carbons in various forms. We've made carbon cloths, and we've made carbon felts, and we've made carbon powders. And we're spent a while trying to decide which type of carbon would be best to use. And the reason for that is the type of carbon that's best to use will fit a manufacturing process. We can't make a carbon that we want to make and then build a manufacturing process around that, because that would cost hundreds of millions of pounds. And we just don't have that. So we need to look at existing manufacturing processes and build our carbon that will perform to fit in with those existing manufacturing processes. And that's a challenge in itself. You may have read about Tesla. Tesla bought Maxwell recently, and they bought Maxwell because Maxwell had something called a dry battery electrode system. What that means is their production method for making the electrode is a dry method. Normally when you make an electrode, you mix up a slurry with something like dimethylformamide or an MP, something like that. You mix a slurry, you cast that slurry into aluminium foil, you dry it, you press it, and out comes your electrode. Well, those solvents, NMP and DMF, are not nice. So they have to be done in a protected environment, they're expensive, so they have to be recovered, and it makes the whole production process very much more expensive. What Maxwell did was take that out and use a dry mix and then calendared it, so that section of production didn't cost as much. And it reduced the overall production cost by 20%, which is huge actually. So it's a huge reduction in cost by using a dry mix that they press on to the electrode. And that's why Tesla bought Maxwell for that piece of technology. And he paid $200 million. These kind of things, because the world market is so large, small changes have a big impact and have great value. Now you think about the supercapacitor market and the battery market, it's in the billions of dollars to almost trillions of dollars in terms of that market value. So it's a very interesting market to absolutely everybody. And they're all trying to get in on it, and small changes make a big difference. So we were looking in the same way that Maxwell were looking at these cost reductions on the production process. So what we decided to do was take the powder and use a traditional paper making process. Now we're actually in negotiation with the paper making company for them to be able to make rolls and rolls of this stuff, but at the moment we're making it by hand. So we hand make these sheets of carbon paper, and that is the basis of our battery and our supercapacitor. The reason that's the basis is it uses a traditional technique with which there's plenty of machinery around and plenty of slack production capability, so it's going to be easy to make massive amounts of this material. When I say easy, it's a relative term. It's going to be easier than doing lots of other ways of doing it. So we can put this into the paper manufacturing process and get rolls and rolls and rolls. And these rolls, remember, are 4 tons each. Rolls of active paper we can use on our devices. Of course, we can then use paper conversion techniques. That is, we can use the existing manufacturing process to cut them into sizes that we need. Now, cutting something into size is a massive challenge when you have 4 tons of it. It's not a problem you've got one piece of A4 and a pair of scissors, you can do that. But try doing that 2 million times, you're going to find it pretty wearing, and try doing it 2 million times where each one is exactly the same size. An impossible task unless you mechanize. And having existing industries with that mechanic capability means that we can slot right in there. So we went for the paper method because we thought it was a good approach to be able to mass produce all of this stuff. We make these by hand. It takes us about 3 days to make 400 sheets. So that's the kind of production capability we have. Not great, but it's good enough for us to be able to demonstrate to a small scale what it is we're talking about. Now what we then do is cut that with a pair of scissors, put a separator in and wrap it around a case. And here's an example of a small one where we've done exactly that. So that's a little bit of paper that you can see standing out there. And this case wrapped around it is actually conductive plastic. So a bit of conductive plastic around that, and we heat seal it and vacuum it out, and that makes our cell, and it's quite stiff and quite a good cell and lasts for ages. This, for instance, for example, is I think it's about 3 months old, maybe 2 months old. It's quite old. Been sitting around for a while because we want to see how that vacuum will hold. Obviously, we really need about 8 years, but so far it's holding really well and we're quite happy with it. One of the problems here is that although this is conductive, it's not very conductive in that direction because it's just too far, but it's quite conductive in that direction because it's so thin. So in order to connect to that device, we can connect one side on here, which is the center plate, but on here we can't really connect to it. You probably can't see very well, but it's quite wobbly. So if we just put a plate on that, actually the contact on there is so poor that a lot of that energy is lost. Now we can still use that, but a lot is lost. So that was one of the problems we faced. And one of the ways we solved that problem was to bright plate it. So we put a bright metallic plate onto that plastic. Now if we connect anywhere on that metal plate and on there, that battery works. Now I've got a little motor just to demonstrate that for you. So if I connect to that tab, I'm hoping you can see the motor. It's right there. And if I take that, that motor is whizzing away, and it will whiz away wherever I touch on that metal case. There we go. So we thought it was really rather cool. There's something else that's really rather cool about that, actually. If I want to make a battery that has more power, all I do is put those together, make sure these are all the same way. They go together, they clip together, and we touch anywhere on that case again, and we have a battery with more current. If we want to make it with more voltage, then what we do is, keeping this long, fold that over, bit of paper or plastic over there, fold that over, and the next one goes so the metal touches the case, and then we fold that over, bit of plastic, metal touch the case, fold that over, bit of plastic, metal touching the case, and now we have them in parallel, so we can increase the voltage. These cells are 2 volts each, incidentally, so 4 of them, that's an 8-volt cell. We connect there, and we have an 8-volt cell. Now these particular ones weigh 10 grams each, and the energy density on them as a capacitor is around about, I think it's 12 watt-hours a kilo, and as a battery, I think it's about 40-50 watt-hours a kilo. But again, we're having that verified. So that's how we would connect them all together to make it in parallel, and remember, in series, you flip those out and connect there, press those together, and that's in series. Now, incidentally, that's really quite a cute cell design, but it is a design, and shown it here means that design, unless it exists elsewhere, is now our copyright. So we have the copyright on that design, incidentally, and that's by virtue of doing this video. So we can make whole loads of those, and we made quite a lot of these small ones to check all that stuff out. Because of course we can't just do it and hope it's going to work, we have to check it and check it and check it, and that's what we've been doing. So we made them in that size, and then we decided to make a really big one, and one whole piece of paper. There it is. That works beautifully too. Bit big, so we're starting to make a standard size like this, and that's kind of our standard size of cell. So that's the size of cell that we're going to be making. Now, there are problems associated with this. Have two solutions. Either we spend the time in-house working those problems out, or we have the money in order to pay other people to do that job for us. And that coating, for instance, we could have got that material sputter coated, but it was like 150 quid for an A4 sheet for a test sample. It's just too much. 6 sheets, that would be, what is that, £900? It's just far too much for us to be able to pay. So we had to come up with a solution that we could use in-house to do maybe 100 of those sheets at next to nothing. And that was one of the things we worked on. So this is a bright plate solution. So that's all it is. It's just this solution. It's a neutral salt. And then we used that and wand plating to create this bright metallic coating. Now I'm going to do a separate video on that because actually that's quite awesome. If you can think about electroplating and bright plating, it's quite difficult to do unless you have a massive tank and some cyanide. So having a very harmless solution there that we can just rub on to create a bright coat, metal coating was quite an awesome thing to have done and quite challenging. So we're going to give a further demonstration on that. So it'll be another video showing you how to use that solution to bright plate, and we're probably going to sell that on the shop to raise revenue for everything else that we're doing. There is another problem that we had, obviously, is this bit of paper. You can't just put it on there because it will fall off. So you need to stick it on there because you've got exactly the same problem in that this stuff is slightly wobbly. This stuff is very wobbly. So if I just rest it on there, I've got a very high resistance between the two. So we had to develop this. This is a acrylic adhesive, a solvent-free, pressure-sensitive, acrylic conductive adhesive. And what you do is you wipe this on, you leave it to dry. Once it's dry, it has a permanent tack. And then we can take the paper and press the paper onto our current collector, come away, and it stays stuck to the current collector. Obviously we use aqueous electrolytes, so this stuff won't dissolve in water either, and creates a junction between the current collector and the active material that can conduct through. So we had to solve that problem as well, and we solved that problem like we always do in-house, and we came up with this pressure-sensitive conductive acrylic adhesive. Again, it's another one I'm going to do another video on because I think there's much more to this, and I'd like to show you that and take more time on another video. It is also another material we're going to put on the shop, again, to raise revenues so that we can continue with this. Remember, we have fees to pay, so we need to do that. So we're going to sell those two things, I think, on the shop and do some demonstration videos on them. So that's as far as we've got to, really. We've got to our standard size and our method of making our carbons, and we are just a spit away from producing these things. So what do we need still? Well, we still need somebody to mass produce this, and as I say, we're talking to a couple of companies, actually, a couple of paper making companies to mass produce that so that we can cut it up. We also need somebody to cut it up, obviously. We can assemble it, so we're fine to assemble that stuff. And then once we get to that stage, we're looking at actually delivering those devices out. So I hope that was of interest to you, and I hope it tells you where we are with things. Any questions, obviously, feel free to ask because I will answer them. You know me, I answer everything. So feel free to ask, and I hope that keeps you up to date, and thank you very much for watching.